Hi everyone, Mrs. Pasega here, and today we worked on how the electric force and gravitational force are both field forces. In both cases, the gravitational field creates a gravitational force on a mass, just as an electric field creates an electric force on a charge. So let's look at that more closely. Let's start out with gravitational field, whose symbol is G. The little arrow on top of G indicates that gravitational field is a vector and it has direction. Now, you and I have been working on gravitational field for a long time. This concept was first brought up in September, and we started talking about that this gravitational field is the distortion of space around an object with mass. All objects with mass have a gravitational field, but it's only important for really massive objects like the Earth because those are the only ones with a big enough distortion of space around them to bend other objects towards them. What I want you to think of for gravitational field is it's how much gravitational force a kilogram of mass put at that location would have. Now, with a gravitational field of 9.8 newtons per kilogram on Earth, that means every single kilogram of mass in that field would experience 9.8 newtons of force. On the moon, that 1 kilogram of mass would only experience 1.6 newtons of force. And the vector means that it points towards the center of mass. It has a direction. That's what this little arrow on the top indicates. Now, you and I didn't draw gravitational field lines for the Earth because that would be kind of boring. I want you to imagine this mountain setup that I have in the bottom here. A is on top of a mountain, B is in a hill, D is on the ground, and C is up in the air. All of those locations have a uniform gravitational field. Notice how the gravitational field would all point straight down towards the center of the Earth, and it would be 9.8 newtons per kilogram at each of those points. If I then brought a water bottle to those fields, like I climbed up the mountain and I brought it to point A, this water bottle would have a force. So the field creates a force on a mass. And notice that any 1 kilogram water bottle brought to these locations would all experience the same force. In the case of the gravitational force, it sometimes has this other word, weight, which we use interchangeably with gravitational force. So the field is the distortion that creates a force acting on a mass. That's what this equation from back in the day means. The gravitational field, G, bends the space. And it bends the space pulling on masses in that space so that those little masses experience a gravitational force. Fg equals mg. Since those arrows point in the same direction, G points down and Fg points down. We didn't really do field lines for Earth because it would be kind of boring. If you're near the surface of the Earth, all the lines point straight down. If you're far away, they kind of all point in radially like a circle. Okay, but now let's add in electricity. Electrical field is going to have a symbol capital E. It has an arrow too because that indicates it's a vector. Its units are still newtons per coulomb this time, but that's because the electric force acts on charges. Coulomb is the unit for charge, instead of kilograms of mass. So just like before, electric field distorts the space around any object with charge, with a net charge. And if I put a charge into that field distortion, that second charge would experience an electric force. So let's say I have a capacitor that has an electric field of 300 newtons per coulomb. That means every coulomb of charge that enters that field would have 300 newtons of force acting on it. But unlike the gravitational field, which always points straight down towards the center of the Earth, an electric field is a little trickier because we can have more complex arrangements of charges. So, as a rule, your electric field lines should always point away from positive charges and towards negative charges. They point in the direction a positive charge would experience a force. I want you to imagine in your head, instead of having a simple distortion around the Earth, right, where it all points in the same direction, what if you had some positive charges indicated by these little mountains here, and some negative charges indicated by these valleys? We would want a way to express those distortions easily. Enter the electric field diagram. In electric field hockey, the game we were playing, we were making charges like this, and then we were tracing the field lines. So we were connecting up these dots, right? And notice that the lines point away from positive charges and towards negative charges. So that means if I take these two rules put together, I can determine the sign of charge on each object. Try it for me now. Which ones are positive and which ones are negative? Did you say blue is positive? Well, that's good because notice that all the arrows leave. They're pointing away from blue, so blue must be positive. And red must be negative because all the field lines point towards them. This type of diagram is also useful because the more field lines you have in an area, the stronger the field. Now, this type of diagram falls flat and it can't tell you the number associated with the field, but it can tell you that this location here is stronger than over here, for instance, because at A, the lines are close together, so stronger field, and at B, the lines are far apart. There's no lines nearby even, so smaller field. Notice also this means the lines can't cross each other, because if they crossed each other, that means a positive charge at this location would move in two directions at the same time. It can't do that. It can only move in one direction at a time. So the field lines cannot cross each other. This is one special arrangement called a capacitor. A capacitor is still going to obey all these same rules, but I want you to notice that inside a capacitor, all of these lines are straight. We call this a uniform field. And notice this looks like the uniform field of the Earth. All of my arrows point straight down. Well, that uniform field means that we can use this new electricity equation, which we'll work on tomorrow. You should be able to, after this lesson, draw electric field lines from arrangements of point charges, knowing that they point away from positive and towards negative. You should be able to interpret field lines, showing that it's strong where there's a lot of field lines and weak where there's not many. You should be able to point out problems, like if you see a field line diagram where the lines cross each other, you should be able to point out that that is not correct. You should be able to draw the straight line field inside a uniform electric field. And finally, you should be able to sum up this big main idea. The main idea of this video is that a gravitational field creates a gravitational force on masses that come into that field. In the same way, the electric field distorts space around charges. Any other charges that are brought into their vicinity have a force that acts on them because of that distortion of space. Furthermore, we represent that distortion of space using electric field line diagrams as shown. All right, everyone, best of luck!